Welcome back. This is week 13 of Graduate Statistics, University of Cincinnati. We'll continue our class on multiple regression. So we are working on interpreting a multiple regression model that tries to explain poverty based on two predictors: the percentage of white people that lives in a state and the percentage of households that have as head just one female breadwinner. So these two variables, as we mentioned, are correlated with each other, which means, and actually strongly correlated with each other, which means that when they're together in the model, there is a chance that even though each of them independently, are related to poverty, it's possible that after controlling for one, the other does not, no longer shows up as important to the model. And that's precisely what happened in this case. There is a correlation between poverty and percentage of white people, negative correlation of 0.31, a reliable, statistically significant correlation. And there's also a significant correlation between the percent females in a household, the percentage of females that are heads of households by themselves, and poverty. That's a 0.53. However, when both of them are in the model, and when the percentage of the percentage number of females that are head of households are controlled for is fixed, varying the percentage of white people in a state does not impact poverty. On the other hand, if I fix the amount of white people in a state and I vary the amount of females that are heads of households, it still has leftover variance to explain poverty levels, right? So when we control for the number of white people in a state, females, the number of females that are heads of households by themselves is still a reliable predictor of poverty. So interpretation for this was provided in the previous video, so go back there if you're curious. All right, let's go to a different example. Modeling cognitive test scores of children. So here's a question we could ask. Are children's cognitive performance related to a particular characteristic of their mothers? We have data. The data that we'll look at the results of are data from cognitive test scores of 3- and 4-year-old children. That's their measure of children's cognitive performance, and characteristics of their mother, a number of them from a subsample of the National Longitudinal Survey of the Youth. So here it is. So here are the kids' score. So that's our response variable. And here are the characteristics of the mother. We have whether or not mom went to high school or graduated from high school. That's a categorical variable. We have mom's IQ. That's a numerical variable. We have a variable that represents whether or not mom works. There's a yes or no. And mom's age. That's a numerical variable, and this one is categorical. All right, let's look at the model. Let's put in all of the variables in and see what happens. So when the 4 variables are there, when I look at each one of them, I must think to myself, what's the contribution of whether or not mom went to high school when all of the other variables in the model are held constant, right? If all of the other variables are held constant at their average level, say, how much do I modify? How much modification do I get in the children's cognitive performance when I vary that particular predictor? Okay. So it does something quite special when all of them are present in the same model. And it doesn't matter the order that you enter them. If you're running a simple regression, every one of them The coefficients estimated for every one of them represent their contribution when the others are held constant. All right, so now, and this is true what I just said, that order of entry doesn't matter when you're running a simple regression. There are other ways of running regression which are beyond the scope of this course, that you can put one variable in, let it absorb all the variance, and then put the other one to see if that adds to it, but it's not what this one is doing. This one is assessing the unique contribution of each one of them, while the others are controlled for or held constant. Okay, so look at the model. We see estimates for all of these variables. We see that the model is explaining about 21% of the variance in children's cognitive performance. Again, it's a very complex construct, so explaining 21% of its variance is not negligible, and it is reliable, which means that I do better with this model in predicting cognitive performance than I would do by just guessing, right? All right, so let's go on to interpret each piece. There are only two variables that seem to have unique contributions to this model, which is whether or not mom went to high school. And because we have yes here, we know that R picked no as the baseline for comparison. And the estimate being positive, it says that children score, children who, when IQ is fixed, children whose mom went to high school score 5 points higher, right? For each, yeah, scores 5 points higher in the cognitive test, right? So, and it is, this particular one is significant predictor. Now, the other variable that is a significant predictor of the child's cognitive ability is the mom's IQ. And this is saying that for each unit increase in the mother's IQ, the score in the cognitive test of children, of their children, increased by 0.56, and that's significant. The other two, you see how these values are different from 0, but they're not different enough for us to assume that they're unlikely under the hypothesis that they are 0. It's just sampling error because the p-value is less than 0.05, right? So again, we're looking at the full model results down here, and here we look for the contribution of the individual predictors. And we should only be interpreting and paying attention to those that are reliably, that we can assume that they're not 0. All right, so in order to give you the idea of what hypotheses are being tested, the age O hypothesis that the model as a whole is testing for that p-value is that all betas are equal to 0. That's the null hypothesis. Because this p-value is less than 0.05 for the whole model, that tells us that we dismiss this hypothesis in favor of the alternative hypothesis that at least one of the betas, at least one of the model coefficients, is different from 0. Okay? At least one of the slopes is different from 0. And we have the individual t-tests here to tell us which one of them are actually different from 0. So we don't do the contrast analysis in the same way that we do ANOVAs. We have some t-tests on the coefficients themselves. All right, so for each slope, I make I make a hypothesis test and make an inference about whether or not we're going to consider it relevant for predicting the dependent variable. And then the hypothesis there is individual for each one of them, right? Age 0 is that beta n, beta 1, for instance, equals to 0, meaning that we will assume whether or not mom went to high school is 0. That's the null hypothesis, when all other variables are included in the model and held constant. An alternative is that beta And as an example, whether or not mom went to high school is different from 0 when all other variables are included in the model, which means when all other variables are held constant, right? How much change will I see in children's cognitive performance when I go from mom not having to mom having high school degree, okay? And we do the same for each one of them in isolation. And we can see how we reject the null hypothesis that beta is 0 for mom having high school diploma, mom's IQ, but we do not reject the null hypothesis for these other two. All right? So this is just a little bit repetition, but one more time with feeling. Whether or not mom went to high school is a significant predictor of cognitive test scores of children after controlling for all other variables in the model. When we hold all other variables constant, there's still a leftover contribution of whether or not mom went to high school to children's cognitive performance. But the other ones, these other two down here, are not significant. So we could potentially then trim the model and take them out because they're not contributing to the model, but we have them there, which somehow affects a little bit what the other two variables do. So you could remove them to the model and watch what happens to R adjusted. If R adjusted doesn't drop too much, then it's better to have them out and have a more parsimonious model. So one method we call backwards elimination. So the R-square adjusted for all of this model is 0.21. If we remove the variable that has the highest p-value, then we run the model again. We can see how it even improved R-square adjusted because, you know, we have less variables and we're still explaining more or less the same. Sometimes you can have an increase in the R-square adjusted because this model was being penalized by having two variables there that don't work for the model. If we cut this one, we have just the two significant variables. It's still better than here, and it doesn't change much from the other one. So this would be your most parsimonious model because we basically still have our 21% R-square, meaning that our model still explains about 21% of the data. That didn't change from here to here to here, but we have a more parsimonious model with potentially better estimates, more precise estimates of the variables that stay in the model. All right. So that's it for the lecture portion. Now we're gonna go work on the lab portion. I'll record a video working through one other example that we can use to think about regression and how to model interesting response variables. I think this is one of the most used types of analysis in a lot of the work that you will read. So it's nice to get a good grasp of what it does with multiple examples. All right, see you in the lab. Bye-bye.